All right, hope everybody's doing well. Let's start off with the homework. Let me get this set up. So, well, let me start with a few administrative things first of all. So for whatever reasons, last class the video did not kick in. So I did not have video recordings from Monday's class when we started talking about graph theory. So I went ahead and pulled some video from when I went over this last year and posted that. So that's why there's 2019 videos on the playlist for Monday. But I think it covered basically the same things. But we'll be going over everything today. But anyway, that's why there's the weird date on the videos. The other thing I wanted to mention, and we'll get into this more next week, but just kind of an advanced heads up. The Monday after Thanksgiving, so this will be week 11, that Monday class, I have a meeting that I apparently can't get out of at 1 o'clock. So we'll go ahead and we'll meet from 12:30 to 1. But I'm going to leave a video on Canvas and ask you to spend that remaining 50 minutes of class time going through that video. Okay, because I don't want to give up an entire class. And at that point, if we skip Monday's class, it would have been 9 days from next Monday till the Wednesday after Thanksgiving. So I'll mention that again on Monday, and then I'll mention it, the Monday that we're back from Thanksgiving. But part of that class will be just an online video that I'll ask you to watch as if it was a regular lecture. Other than that, business as usual. Any questions before we go over and talk about the previous homework? And well, we can also run through the new homework. But I'm hoping that after today we'll have gotten through almost everything we need for the new homework, except Dijkstra's algorithm. Dijkstra's algorithm will probably wait until Friday. But let's just run really quickly through the previous homework. So these were different questions related to permutations and combinations. And by and large, most people did well. Well, everybody did well on this. By and large, most people seem to not have a lot of trouble with it. The main difficulties, there were three difficulties. One, knowing the difference between a permutation and a combination. Okay, permutations are ordered. Combinations are unordered. If you want to remember that, just remember combination locks should really be called permutation locks. Because with a combination lock, the order of the numbers matters, right? So just think of going to your locker and unlocking your permutation lock, and you'll remember permutations are ordered. So if you need to pick 3 people to receive, one of 3 different awards, first place, second place, third place, right? You're selecting 3 people out of 1,000, for example, but the way in which you select those 3 is significant, right? Choosing one person to get, choosing person A, B, and C to get first, second, third place is different from choosing person A, B, and C to get third, second, and first place. Okay, so if order matters, you're probably using a permutation, and that's really just a variation on the product rule. If the order doesn't matter, you can think of it as a permutation divided by the number of ways you can rearrange things, right? So you have that extra component. So permutation of, NC is n factorial over n minus c factorial. And combinations of NC is n factorial over n minus c factorial times c factorial, which is just the number of permutations divided by the number of ways you can arrange c things. So with that in mind, question 1, 1,000 tickets, and you're going to award 3 prizes, and the order in which those matter, because it says there's 3 different prizes, so that's a good old permutation problem. Right, which is 1,000 factorial over 997 factorial, which you can do with a calculator. You don't need to calculate 1,000 factorial first. You can write this out. Right, so that's what 1,000 factorial looks like, and this is what 997 factorial looks like. And all of this stuff is going to cancel, and that's what you end up with. And again, that's just the product rule, right? 1,000 ways to assign first prize, 999 to choose someone for the second, 998 to choose someone for the third. So that's really just capturing that idea of doing a product and the diminishing multipliers as you go. So that was question 1. Okay, so biggest problem was mixing permutations and combinations. Second biggest problem was not reading the problem correctly, and third was simply not doing the problem at all. So those were most of the point deductions. So 3 was a question where some people didn't read the problem or follow it fully. So how many 8-letter words can be formed from the 26 letters of the alphabet, even without concerning ourselves about whether words make sense? There's 2 interpretations of this problem. Answer both. And we talked about this a little earlier. 2 different interpretations, with or without repetition. In each case, you have 26 letters. You're trying to form an 8-letter word. But the question is, do we allow words like this? Or are we allowed to only use each letter once? All right, so if you're not allowed to repeat a letter, then this is a simple permutation question where you have 26 letters and you're trying to pick 8 of them, and the order in which you pick them matters. All right, so that's a permutation. But if you're allowed to do repetition, then it's not a permutation or a combination question, but you can still solve it by going back to the product rule. 26 ways to pick the first letter, 26 ways to pick the second, 26 ways to pick the third, and so on. This will be 26 to the 8th. All right. Also, on most of these questions, people did, show me what they were doing before they went on and wrote down an actual number. That's perfect, right? You always want to do that. Write down the formula, write down the expression, the calculation that leads you to the answer, and then if you want to put in a numeric answer, go ahead and do that too, and that's helpful for grading. But, if you miss a digit or something, I can go back and see what you were doing. You usually get credit for that. All right. I blew past a few questions, though. Question 5 and 2-1. 6 officers taking their picture. How many different ways can they be arranged? Here again, the fact that they're in 2 rows is really kind of a bit of a red herring. We can really think of 6 positions in which you're going to stand people, and it's really no different from just standing people side by side. It's basically, let's take these officers, there's 6 of them, and let's figure out how many ways we can arrange them. This is just P66, which is good old 6 factorial, 720. All right, and then question 15, you're making a meal. You have a choice of a main dish, which is fish, lamb, or beef. So there's 3 ways to choose your main dish. You can choose peas or carrots for a vegetable, 2 vegetable choices. And pie, cake, or ice cream for dessert. So 3 types of desserts to choose from. Notice there's more desserts than there are vegetables. So that's the total number of ways that you can select your meal. So 3 times 3 is 9, that's 18. All right, so raffle ticket question we did. That's P1000, 3. 8-letter words is either P26(8) or 26 to the 8th. And then the basketball question, we talked about that one previously, but let me do it really quickly again. 2 parts to this one, and some people didn't do part B. So part A, you got 15 people, you got 5 positions, anybody can play any position. So we're trying to pick out 5 people out of 15 in a particular order, right? So this is a straight permutation. Part B, we're told that there's only 2 people who can play one of those positions. So this is a product rule, right? How many ways can we fill the first position? Well, there's 2 ways to do that. How many ways can we fill the remaining 4 positions? Well, we're going to pick one person to take this position, which means now we have 14 people and 4 positions. That's just P14, 4. Yes, always eat dessert first. I agree. All right. So the whole takeaway from this is, being able to think of these things in terms of, can I use a P or a C, or do I have to do something with a product rule, or is there a sum rule kicking in somewhere? Things like that. It's just practice. There's a bunch of these problems in the textbook if you want more practice on them. But it's just kind of getting used to thinking about these questions in terms of how do we calculate the answer. So 2.3 we talked about last week. So I graded questions 3, 5, 15, 1 and 3, and 7. I did not grade the question in 2.3 because we went through that one in class. But 90 people, 47 played tennis, 42 swam, 17 participated in both activities. So this is the principle of inclusion exclusion. So so let T equal a set of people who played tennis. Let S be the set of people who swimmed. I don't know. And so we're asking how many people participated in neither. Well, if we know how many people did swimming or tennis, right, then we can figure out how many people did neither swimming or nor tennis. So we need to know a few things. The entire universe, we're told, consists of 90 people. So the size of the whole universe is 90. The number of people who at least played tennis is 47. The number of people who at least did swimming was 42. And then we're given one key piece of information. 17 participated in both. Well, if you participated in both, then you're in the intersection of these 2 sets, and that's 17. So the principle of inclusion exclusion tells us this. Right, the number of people in the union is the sum of the size of the 2 sets minus the size of the overlap. And so this is just plug in the numbers and calculate. So that's 30, that's 72. So 72 people did tennis and or swimming. And so the size of the complement of that is just the people that are left over. So that's 18. All right, and then section 2.4, I graded questions 3 and 13. So question 1, which I did not grade, let's make sure we're clear on how to do that. Committee is made up of 3 faculty members and 4 students out of 10 faculty and 25 students. So how many committees are possible? Well, it's a product rule. First choose your 3 faculty members. So you're choosing 3 out of 25, sorry, 3 out of 10. And the order in which you choose them does not matter. So this is a combination. Right, so it's the number of, it's 10 choose 3. The number of 3 combinations of 10 objects. That gives you the number of faculty members. And then for the students, you're choosing 4 students out of 25. And the order doesn't matter because the positions are presumably identical. So that's 25 choose 4. And then multiply those 2 answers. And that gives you the total number of committees possible. All right, how many subsets of 110 contain at least 7 elements? So counting subsets, we can think of this as, there's your 10 elements in your set. If you want a subset with 7 elements, we have to choose 7 from this set of 10. And we're just throwing them into a set. They're going inside curly brackets. The order doesn't matter. So the number of subsets with 7 elements is 10 choose 7. Okay, but it asks us for a number of subsets containing at least 7 elements. So we can satisfy the task of finding such a subset in 4 different ways, by either finding a 7-element subset, or an 8-element, or a 9-element, or a 10-element. So this is a sum rule. There's the number of 7 elements. Here's the number of 8. Here's the number of 9. And there's the number of 10-element subsets. So you add those together and you get 176. All right. Binomial expansion question was the other one I did not grade, but that's just plugging in the coefficients from Pascal's triangle. But you're doing 2x minus 3y to the 4th. So it's going to be something times 2x to the 4th plus something times 2x cubed times minus 3y plus something times 2x squared times minus 3y squared plus something times 2x times minus 3y cubed plus something times minus 3y to the 4th. And I believe this is 1, 6, 10. I don't know if I believe I can do this. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This is 1, 4, 6, 4, 1. So this is 16x to the 4th plus 4 times 8x cubed times minus 3y, and you just kind of spell that out. Although, you know, this is technically a correct answer too. So I would at least put this on your answer sheet and then go ahead and simplify it down if you like. All right, and the last question, which we also talked about before, was about number of lines and triangles determined by points. Well, you have 10 points. And we're told that no 3 of them are collinear. And so how many lines are there? Well, the number of lines you can draw corresponds to the number of ways you can pick out 2 points to draw a line through. Right? Well, if we decide to draw a line between points 1 and 4, it's the same line as if we draw between 4 and 1. Right? So the order in which we pick these points doesn't matter. So the number of lines is just 10 points from which we choose 2. And that's 45 lines. And then for triangles, same thing. We simply have to pick 3 points. and the order in which we pick them doesn't matter, so the number of triangles is 10 choose 3, which is 120. So there's always permutation, combination, product, sum rule questions on the exam. So make sure you go over those. Let me know if you have any questions. Remember, I have office hours Wednesdays from 5 to 7. So come by and ask questions if you like. All right, let's take a quick run through of homework 9. And we've gone through some of this, but mostly not. So let me pull this up. I don't have a homework folder. That's okay. There we go. All right, so precedence graphs, we're going to start off by talking about those. And then we're going to talk about adjacency lists, adjacency matrices, and adjacent incidence matrices. So that's going to be our first two topics. That will let you do question 3 and question 4, because here I'm giving you representations of graphs using these different forms. I'm asking you to draw pictures of them. And that will let you do most of question 5, but we're going to talk about how to tell if two graphs are identical. So we'll get through that today. And then probably Friday we'll start talking about following paths. So that will be questions 6, 7, 8, and that will take us up to Dijkstra's algorithm. So let me talk about precedence graphs as another example of a graph, and then we'll talk about representing graphs inside a computer, which will get you through most of the rest of these questions. So what's a precedence graph? The idea here is imagine that you have a computer with multiple CPUs on it. Okay, so you can execute multiple instructions at the same time. All right, so normally a computer, does one instruction, starts it, finishes it, begins the second instruction, starts it, finishes it, begins the third, and so on. So let's write some code. All right, there's some random statements I'm writing down. We're thinking of this as a C program, so these things are going to execute sequentially. I'm going to put line numbers on these statements. And the thing to notice here is that, for example, statements 1 and 2 could execute simultaneously. If we had two machines, we could be writing the number 10 into the memory location where X is stored at the same time that we're writing an 11 into the memory location where Y is stored. This assumes we have what's called multi-ported memory, where you can read and write multiple locations simultaneously. But there's no dependency between instructions 1 and 2. On the other hand, instruction 3 cannot be executed until X and Y have their correct values. If we were to start executing this third instruction before we gave Y a value of 11, Z would not end up with the correct value. So there's a dependency there. All right. This fourth instruction, x, well, this depends on the value of z, which is calculated in step 3, and the value of y, which is calculated in step 2. And 5 depends on the value of x, y, and z, which means it needs to wait until instruction 4 and 3 and 2 are finished. T equals 11, there's no dependency of that on anything. That could happen way back here at the same time that x and y are getting their values. And t equals t plus y can happen as soon as t gets its value and y gets its value. So inside a CPU, there's an instruction scheduler that is looking ahead at instructions to be executed and figuring out, can I do any of these things ahead of time? Do I really have to wait for these first 5 instructions to run before I can set t equal to 11? And if this scheduler can figure out, hey, I can do this t equals 11 while I'm doing these other operations, now when I get to step 7, t's already been set up. So in the 50s and 60s, the big iron days, right? The CDC computers and the Cray computers, this was their secret sauce. This was what made them so fast, in addition to the really energy-hungry ECL transistors inside. It was these advanced scheduling techniques, right? Where you could look ahead and you could break your instructions into smaller steps and do things out of order. Okay, now this happens inside, your Pentium processor. This is hyper-threading. This is all this other stuff that's standard in all modern processors. But at the time, this was a very different approach to executing code because, it's not just a sequential interpretation of what the code says. It's really looking ahead and doing things potentially out of order. So how do we know what's safe to do out of order and what's not? So we can make a graph to represent these dependencies. So each vertex is going to be an instruction. And there's no dependency of instruction 1 on anything. It can happen at any point, and instruction 2 can happen at any point. But instruction 3 needs the results of instructions 1 and 2 before it can execute. So we can draw something like that. And instruction 4 needs the result of instruction 3 because it needs a current value of z. It also depends on instruction 2, and so we could draw an arrow from 2 down to here, but we can also look and see that this is already dependent on 3. Right, but let me put an arrow in here, right, because it needs z and it needs y. Instruction 5 needs x, y, and z. Well, x gets its value up here, and y gets its value right here, and z gets its value here. And I'm making those dotted lines because after I make this graph, I can go through and I can say, hey, if I'm waiting for instruction 3, that's also waiting for instruction 2. So this line I don't really need. And similarly, instruction 3 depends on x, so it's got a dependency from 1. Instruction 6, no dependency on anything. Instruction 7 needs the result of 6, and it also needs the result of instruction 2, which is y. And this could affect the order in which things take place. Suppose I only have one multiply unit, right, or one unit that can do, assignment of a memory location. There may be one instruction on which, 6 different subsequent things depend. And there may be another instruction on which only one thing depends. So I would do that one that has more dependencies first, so that I could continue executing more instructions after that. And there may be a set of instructions over here that look like this and have no connection to this graph. So I could be executing this entire block of instructions at the same time that I'm executing this block of instructions. So this is how schedulers can go about analyzing the flow of instructions in a computer, making decisions about what to do when. Alright, so that's just another example of a graph, and the homework question asks you to look at that for a specific set of instructions. So that's a precedence graph. All right, so let's look at graph manipulations. This is something we'll come back to in a little bit, but as a lead into it, suppose we have a graph. Suppose we have a graph 1 with a set of vertices and a set of edges, and a graph G2, which is a second set of vertices and edges. So we say G1 is a subgraph of G2 if the set of vertices in G1 is a subset of the vertices in G2, and similarly for the set of edges. So if we have we don't really need labels to be able to do this, but if this is a graph, right, this is a subgraph, right, because there's a set of edges and a set of vertices corresponding to this. This would also be a subgraph, right? It happens to have all of the vertices and 3 of the edges. So nothing terribly startling there. All right, so removing an edge. So you have a graph with vertices and edges, and you have an edge E. So we want to make a new graph containing the same vertices, but with that edge removed. And that's really easy to do. So let's say this is our graph. And let's say we want to remove this edge. Just take it out of your set of edges. Okay, so that's edge removal. A slightly more interesting version is edge contraction. And this looks like this. Suppose we want to contract this edge. Well, we go ahead and we remove that, but then we take the 2 vertices at either end and we join them. So these pinch down to a single vertex, And we end up with something like this. If I'm doing this right. Alright, so we get a very different looking graph. Alright, the third thing we can do is removing a vertex. So how do we remove a vertex? One, remove it from the set of vertices, and then remove all incident edges. So let's go back to our graph. And let's say we want to remove this vertex right here. Well, take out the vertex, and then take out any of the edges that were incident to that vertex. And it leaves you with this graph. Alright, so those are some operations that we'll use when we discuss doing operations on graphs. Before we can operate on a graph in a computer, we have to have a way to store it. So representations of graphs inside a computer, and there's a few different ways to do this. So the first is an adjacency list. So let me number my vertices, and let me label my edges with letters. So here's the graph we're going to pick on. Okay, so an adjacency list. I'm going to list each of my vertices, and next to each vertex I'm going to list all the vertices that are adjacent to it. Remember, adjacent means connected by an edge. So vertex 1 is adjacent to what? 2 and 3. Vertex 2 is adjacent to 1, 3, and 4. Vertex 3 is adjacent to 1, 2, and 4. Vertex 4 is adjacent to 2 and 3. And I can think of these as sets. They're unordered. And so this is pretty easy to store in a computer, right? I have 4 vertices, so I need 4 lists. And when we talk about linked lists in Winter, we'll see we can implement this with a linked list, but we could also just have an array and fill in the elements of the array with each vertex that's adjacent to vertex 1 through 4. Right? This is really easy to create from here. Just start with your vertex and see what you're connected to, right? And just run those together in a list. And so that's one way to represent it. There's a second way we can represent this graph. And all of these capture the same information. They just capture it in different ways. Okay? The second way is an adjacency matrix. So in adjacency matrix, we make a 2-dimensional matrix. And we list the vertices along each axis. And we can put in a 1 or a 0 to show whether these two vertices are connected to each other or not. So I'm just going to fill in the ones that are connected, and I'll leave the others blank for now. So vertex 1 and 2 are connected. Vertices 1 and 3 are connected. Vertex 2 is connected to 1, 3, and 4. Vertex 3 is connected to 1, 2, and 4. And vertex 4 is connected to 2 and 3. And the other entries would be zeros. All right, so that's an adjacency matrix, and this is a more common way to store a graph inside a computer's memory. Some things to note about this. First of all, this matrix is what we call symmetric. If you look at, element row, comma, column, it's the same value as the element in, column, comma, row. Right? Assuming that this is an undirected graph. But if we had a direction to these vertices, right, we might have a vertex from 1 to 3, but not a vertex from 3 to 1, or an edge from 1 to 3, but not an edge from 3 to 1. So this can capture directional information. This also gives us an easy way to capture weights. Because instead of just storing a 1 as a binary flag saying, yes, there is an edge from 1 to 2, we could store the weight of that edge in here. And that weight could be positive or negative. And we could just fill in the value accordingly. So this is a really useful way to represent a graph. What's the biggest potential downside you can think of to using this approach, though, from a CS perspective? It's definitely going to be a little slow. There's a reason why. What's the other downside? Yeah, performing operations on matrices. The main thing to remember about matrices, they're two-dimensional objects. So if I wanted to draw a friendship graph that shows, how many people are best friends with other people, and I want to do this across the entire planet, there's 8 billion people on the planet, that's going to be 64 billion entries in my matrix. And there's nowhere close to 64 billion friendships in the world, unfortunately. Most people might consider themselves close friends with, a handful of people, which means that in this first row there's going to be 8 billion columns. Maybe 10 of those will have ones in them, and the other 7 billion will have zeros. And person 2, may have 100 friends, right? But most of those 8 billion rows are going to be zeros. So this tends to lead to what's called a sparse matrix. Now just the memory to store 64 billion binary flags is huge, right? It's 6 times 10 to the 19th bits. That's a lot. Fortunately, there's a lot of good research and development that's gone into being able to represent sparse matrices and work with sparse matrices efficiently, because this comes up so often, right? If you have a portfolio of stocks and there's connections from one to another, again, there may not be direct connections between most pairs of stocks, but if you're managing, a portfolio of 5,000 stocks, that would be, 5,000 times 5,000, 25 million entries in here, most of them zero. Now, if you have to do something with that matrix, right, that gets to be computationally intense, unless you take advantage of the fact that most of these things are zeros. So there's a lot of good work around sparse matrices. Yeah, 8 billion connections is a lot. How many people know about the Oracle of Bacon? All right, we'll talk about the Oracle of Bacon on Friday. Um, degrees of separation. Was that in the video I posted? Okay. I gave away the goods. Yeah, we'll play with that on Friday. Third way to represent graphs inside a computer, instead of an adjacency matrix, we can do an incidence matrix. Yeah, exactly. Degrees of separation from Kevin Bacon. Incidence matrix. Let's go ahead and make another matrix that looks like this. We're going to list vertices over here, but we're going to list edges going across. So this will be edge A, B, C, D, and E. And now we're going to fill in for each row a 1 anywhere that there's an edge that's incident to that vertex. So vertex 1 is incident to edges A and E. And vertex 2 is incident to A, B, and D. Vertex 3 is incident to C and E. And vertex 4, B and C. And this is still likely a sparse matrix, but it's a different representation of the information. All right, so this we can store, in our computer with a bunch of arrays, or once we learn about linked lists, we can do this with linked lists, and that's a very efficient way to store information. These can be two-dimensional arrays, right? If you have n vertices, this is an n by n array. If you have n vertices and m edges, this is an n by m two-dimensional array. And you initialize it to zeros and you fill in where the ones are. These representations give you some really nice processing capabilities, though. For example, suppose we want to know, well, if we want to know how many vertices there are, right, it's just the dimensions of the matrix. Or for an incidence matrix, number of vertices, number of edges. That's just the dimensionality of the matrix itself. If we want to know the degree of a vertex, right, over here we can just add up across the row. So the degree of vertex 1 is 1 plus 1 is 2. The degree of this vertex is 1 plus 1 plus 1 is 3. The degree of vertex 3 is 3. The degree of vertex 4 is 2. The sum of the degrees of all of the vertices would be the sum of all the ones in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you add up all the ones and zeros in here and divide by 2, you get the number of edges. Because of that theorem we had that the sum of the degrees is equal to twice the number of edges. Well, if you add up all the ones and zeros, you get twice the sum of the degrees. Now, if we want to find a path from one point to another, we can do this with either of these forms. For example, suppose we want to find a path from vertex 1 to vertex 4. Well, we can start with vertex 1 and there's no path to 4. But we know from vertex 1 we can get to vertices 2 and 3. So now we can solve a subproblem. Is there a path from vertex 2 to vertex 4? Well, let's look at vertex 2. Yeah, there's a path to 4. So this is where we can use our recursion, our passing off problems to friends to solve for us. I want to get from here to there. Well, I know I can get from 1 to either 2 or 3, so I'll find a friend and I'll say, hey, can you find me a path from 2 to 4? And I'll find another friend and say, hey, can you get me a path from 3 to 4? And if either of them come back and say yes, then I know I have a path from here to 4. If I want a shortest path, if I have weights, right, I ask each of these people, tell me the shortest path from 2 to 4 or the shortest path from 3 to 4. I take the distance they report back and I add, the distance from 2 to this distance, add the distance from 3 to this distance, whichever one's smaller, that's my shortest path. So I can solve that traveling salesperson problem in about 5 lines of code. I just can't do it efficiently. But to actually find the solution, pretty trivial. If you think of it in terms of recurrence relations and solving subproblems, putting those solutions together to solve the original problem. And writing the actual code to do that, if you have something like an adjacency matrix, pretty simple, right? Can I get from vertex 3 to vertex 4? Yes, because there's a 1 there. Can I get from vertex 4 to vertex 1? No, not directly, because there's a 0 there. So how would I find a path from 4 to 1? Well, if there's a 0 there, then I'm going to say, hey, someone find me a path from 4 to 2. Someone else find me a path from 2 to 1. Someone else find me a path from 3 to 1. If both of those come back and say there's no path, then I know there's no path from 4 to 1. All right, so let's talk about isomorphisms, and then we'll talk about paths and graphs more. Well, let's talk about isomorphisms. So I commented last time that the way we draw a graph on paper is not part of the essence of what that graph is. So here's one graph. Here's another graph. These are the same graph. Okay, no difference between them. Here's another graph. It's exactly the same. So we would say these 3 graphs are isomorphic to each other. And sometimes you'll see a symbol like this. That means isomorphism usually. So isomorphism, similar form, right? Iso, same, morph is form. So in what sense do these have the same form? In the sense that if these were connected by rubber bands that could stretch infinitely, I could deform this shape into this one, right? I could just pull these up here and round out this line down in the bottom, and I'd have this. And if I tilt the whole thing and I take this and I push it down and I round these 2 pieces out, I can make it look like that. But this is not the same form as this. Or this. Or this. So we have to have the same number of vertices and the same number of edges. Awesome observation. All right, so there's a graph with 4 vertices and 6 edges. There's another graph with 4 vertices and 6 edges, not isomorphic. So there's this question of how do you know if 2 graphs are isomorphic? And they may not always look the same to us, so remember, these 2 graphs are isomorphic, even though they look different to us. So the number of edges that cross over each other doesn't tell us if they're isomorphic or not. The number of dots that are in a row with one another or things like that, you know, related to the physical layout, definitely doesn't tell us. there are some things that must be true if graphs are isomorphic. So we have these invariants. And invariance is a general term for things that are preserved, things that don't vary when you move from one thing to an isomorphic thing. So graph invariance, so number of vertices, number of edges. If two graphs have a different number of vertices or edges, guaranteed they're not isomorphic. Right, those have to be preserved. And that's the rubber band thing, right? You're not adding or removing rubber bands, you're not adding or removing thumbtacks, you're just moving them around. So those have got to be the same. The collection of degrees of vertices has got to be the same. So for example, each of these vertices have a degree of 2. Each of these vertices have a degree of 2. Okay, that's encouraging for the possibility that these are isomorphic. On this graph up here, I'll just write the degrees next to each vertex. Each vertex has a degree of 3. Whereas here our degrees look like 2, 3, 3, and 4. So this collection of 4 3s is not the same as this collection of 2 3s, a 4, and a 2. That guarantees they're not isomorphic. And again, thumbtacks with rubber bands, right? If we have 5 rubber bands coming out of this thumbtack, it doesn't matter where I move that thumbtack, those 5 rubber bands will always be connected to it. The degree is never going to change. But this is still not enough to guarantee that that your graphs are isomorphic. And in general, it's a really hard problem, being able to just take 2 graphs and have some kind of turn the crank thing and know if these things are the same graph or not. But we can use some of these representations to help us do this analysis. So so let's look at these 2 cases here. And let me label these. So now I'm going to label my vertices with letters. I don't know why. And here's my first graph. And here's my second graph. I'm going to draw an adjacency matrix. Let me use different labels on here. Let me call these W, X, Y, Z. I'm going to switch to pencil because I know I'm going to mess up. So A is adjacent to B and C. B is adjacent to A and D. C is adjacent to A and D. And D is adjacent to B and C. So there's an adjacency matrix for that graph. Over here, W is adjacent to X and Z. I missed one here, B and C. X is adjacent to W and Y. Y is adjacent to X and Z. And Z is adjacent to W and Y. So there's the adjacency matrix for that second graph. Isomorphism between these graphs can be related to equivalence between these matrices. Now, they're not exactly the same matrix, right? This is a 0, 1, 1, 0. This is a 0, 1, 0, 1. Right away, we see these matrices are not the same. But here's our useful result. So two simple graphs. So this is where we have, just maximum one edge between vertices. Two simple graphs, G1, which is, vertex 1, edge 1, and G2, which is vertex 2, edge 2, are isomorphic if and only if there exists a bijection that's a one-to-one map, F from V1 to V2, such that A and B are adjacent in G1 if and only if F of A and F of B are adjacent in G2. What does that mean? Can we rearrange our vertices? Can we come up with a mapping from the vertices over here to the vertices over here, which give us our original adjacency matrix? All right. Can we rearrange our vertices? Can we map A, B, C, D to X, W, X, Y, Z in a one-to-one onto way, right, bijectively, one-to-one correspondence? Can we find a mapping or a renaming of these vertices to those vertices so that we end up with exactly the same adjacency matrix? And if we can, then those graphs are isomorphic, and if we can't, then they're not isomorphic. And in this case, the answer is yes. So let's do the following. Let's take A and map that to W. So A is going to map to W, B is going to map to X, C is going to map to Z, and D is going to map to Y. Well, if I map A to W, it really just means I'm renaming this column to BW, right? So let me take our original matrix. And these are called A, B, C, D, A, B, C, D. All right, if I map vertex A to W, I'm really changing the names of these to W. If I map B to X, well, I'm just changing that to an X. If I map C to Z, I'm changing those to Z. And if I map D to Y, then I change this to Y. So under this mapping of vertices, this is my adjacency matrix. Is this the same matrix as that? Well, I can't compare them directly because I don't have things listed in the same order. But if I were to swap these two columns, then I would have W, X, Y, Z across the top. So that would give me the following. So I'm going to keep the same thing over here. But I'm going to swap these two columns. So this is going to be 0, 1, 1, 0, and then 1, 0, 0, 1. And I still can't compare this to this exactly because I don't have the same order of my rows. I have YZ here, but I have ZY here. So I'm going to swap these two rows. I'm not changing any of the information represented in this matrix. I'm just drawing it in a different order. So this first row will be the same. This second row will be the same. But I'm going to write the Y row here for the third row. That's 0, 1, 0, 1. And the Z, that was this row right here, 1, 0, 1, 0. And now if I look at this and this, my rows and columns are labeled in exactly the same order, and the ones and zeros have the exact same pattern. Now I know that those are isomorphic. If you cut past the details, all we were doing was rearranging rows and columns. So if we just look at the ones and zeros in here, can we rearrange rows and columns in a way that turns this into that? The trick is if I swap, columns 3 and 4, I also have to swap rows 3 and 4. If I interchange columns 1 and 3, I have to interchange rows 1 and 3. But if I can do that and end up with this matrix, then those two graphs are isomorphic. The downside of that is how many different ways can I rearrange the rows and columns of this? A whole bunch. Right? There's a permutation combination question in there. How many ways could I rearrange the rows and columns? Well, it's a lot. So again, this is an algorithm that's easy to do, but really, really expensive computationally. This is classic graph theory. So many of these things, very easy to write a piece of code that will do it, but that code may never finish on any kind of reasonable sized graph. So a lot of the interesting work in graph theory is trying to come up with either more efficient algorithms for doing something, that would be the computer science side, right? Or coming up with a different approach to analyze something other than kind of the brute force. Let's just do this the way that occurs to us first off. I don't actually know what the number would be there. How many ways can we rearrange these? I mean, I can swap this first row with 3 other rows, and then presumably swap the second one with 2 others, and the third with 3 others. So it might be a factorial, but I think we're probably getting some other, maybe getting some redundancy in there. But a factorial or an n to the n usually feels right for graph theory stuff. But that would be an interesting question. All right, let's see. Long question in chat. Looking at some of our homework, and some of these matrices seem odd. For example, there's a 1 on the top left of the matrix of problem 4. If we use the ideas we're using here for matrices, that would make A adjacent to A, which is confusing. Yeah, so, So what about a graph like that? Right, so the adjacency matrix would be the following. A is adjacent to A and B and C. B is adjacent to A and C. And C is adjacent to A and B. So you can definitely have edges adjacent, vertices adjacent to themselves, because you can have these loops. So on the homework, right, so construct the 3 representations of this graph, right, so that's just applying these to that particular graph. Draw an undirected graph for the following adjacency matrix. So choose labels for your vertices and, draw the corresponding graph. For question 4, this is not a symmetric matrix. Okay, for example, there's an edge from vertex 1 to vertex, there's no edge from vertex 1 to vertex 4, but there is an edge from vertex 4 to vertex 1. So this is a directed graph, and you can take the direction to be, from row to column, and so draw a directed graph corresponding to that. All right, and then question 5, draw graphs corresponding to both of these. They will look different on paper. I ask you to label this vertices here ABC, the vertices here XYZ, and then tell me if those graphs are isomorphic. If they are isomorphic, you should be able to find a mapping from ABC to XYZ. So tell me what that mapping is. If they're not isomorphic, tell me why not. For example, they have different degrees, different set of degrees of the vertices. So that's an isomorphism question. All right, and then the last two questions deal with paths. But before we go on to paths, questions about this, representations of graphs. All right, well, let's talk about paths. And as with many things in this course, you know, if this was a math course, we would fill up a board with definitions and formal descriptions of this. But I'm interested in the idea of this, and we don't necessarily need to get particularly formal about it. So let me give you an informal notion of what a path is. Suppose you want to get from one vertex to another. Let's say we want to get from vertex A to vertex F. And in traveling through this graph, we're allowed to follow edges. But we can only travel along an edge. So there's no way to go directly from, say, A to F, because they're not connected by an edge. But I could go from A to B to D to F. Right? That's a path. A, B, D, F. I have another path. I could go A to C to D to F. I could also go from A to E to F. I could also go from A to E to G to F. Lots of different paths. I could go from A to B to C to D to F. That looks like that. I could go from A to B to C to E to F. A, B, C, E, F. I could go A, B, D, C, E, G, F. A, B, D, C, E, G, F. I could go A, C, E, F. Lots of different paths. Okay, so you know, formally a path would be a ordered collection of edges with the property that you know, each edge begins at the vertex where the previous edge ends, with the first edge beginning at the source vertex, etc., etc. But really, it's just, you know, start here and just follow edges. All right, that gives you a path. A couple of things that we're usually going to be interested in. One is finding a shortest path. And if this is an unweighted graph, a shortest path would just be the shortest number of edges. We're effectively treating all of these things as having the same weight. Let's just say a weight of 1. So what's the total cost of this path? It's just the number of edges. So a shortest path would be A, B, D, F. That's 3 edges. A, C, D, F, same thing. The shortest path of all would be A, E, F. Okay, that basically takes 2 edges. So that's one thing we're interested in sometimes, is finding a shortest path. More interesting when there's weights associated with these, even more interesting when we have negative weights. The other thing we're interested in sometimes is a path that visits every vertex, such as this one. A, B, C, or A, B, D, C, E, G, F. And we may or may not restrict ourselves to loops. If we allow loops, here's a path from A to F. A, B, C, A, B, C, A, B, C, E, F. And we went oink, 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 bam. It's still a path. But if we want a path that visits every vertex, we may ask, is there a way to do that without any loops? And in this case, yes, here's a path that doesn't have any repeats, doesn't have any loops. But if we just want any old path that visits each vertex, right, I could go A, B, C, A, E, A, C, D, F, E, C, B, A, G. So sometimes we're interested in the shortest path that visits all of the vertices. That's a traveling salesperson problem. Shortest path that will hit every vertex in the graph. And this obviously only works if your graph is connected. If I have a vertex over here, an I, so these are off on an island somewhere, right? There's no way to get from A to I. So we're kind of necessarily talking about connected graphs where every vertex has some path to every other vertex. These loops are why negative weights make this so interesting. Because suppose, you know, I just throw in some distances here. Right, and if I go A, E, F, well, that's going to be 4 plus 12. That's going to be a cost of 16. Whereas if I take this slightly longer path with 3 edges, that's just 2, 3, 4. That's a shorter total distance. But if I have negative weights, you know what I can do? I can start doing loops around here, right? That's 2 minus 6 is minus 4, plus 1 is minus 3, plus 2 is minus 1, minus 6 is minus 7, plus 1 is minus 6. Every time I go around this loop, my total cost gets more and more negative. So if this is how much I have to pay to travel along this edge, and this is how much I get paid to travel along this edge, what's my best route to node F? Well, I'm going to go around here about 1,000,000 times, and I'm going to get close to, you know, $3 million for doing that, and then I'll pay $2 and go over to F. And so that's why these shortest path algorithms get totally wonky if you have negative weights. All right, so we'll talk about different kinds of paths and look at some criteria for when we have paths with certain properties. We'll talk about Euler paths and Hamilton paths, and then we'll talk about Dijkstra's algorithm. That'll all be on Friday. And that will pretty much do us for graph theory. And then Monday we'll be able to get started on languages and grammars. All right, and the definition of a path, I didn't define it formally, but basically a path from A to G would be a collection of edges that let you start from A and go from edge to edge and get to G. But the formal definition takes a lot more work, but really just, you know, follow edges. All right, cool. Have a good afternoon. Enjoy the rain. I will see you next time.